Assalamu alaikum wa rahmatullahi wa barakatuh, and very good morning to all. So, this is the lecture number 8 about concept application of stability and kinetics. In this lecture, we will discuss some points related to stability, and by the end of the lecture, you are expected to be able to describe factors affecting the degradation of pharmaceutical products, and hence affecting the rate of this degradation reaction. You should know the kinetics of drugs composition, know the accelerated stability and stress testing, understand the concept of Q10 that is used for estimation of drug products half-life, and describe the physical instabilities, possibilities that may occur in dosage forms, in pharmaceutical dosage forms, and understand the instability possibilities in different formulations. As we mentioned in our previous lecture, drug stability, defined by the US as the stability of pharmaceutical products, is defined by the US as the extent to which a product retains within specified limits and throughout its period of storage and use, which is called shelf life, should retain the same properties and characteristics that it possessed at the time of its manufacture. So we mentioned last time that we have three aspects: physical stability, chemical stability, and microbiological stability. They should be retained within specified limits. That means there may be some variation with time during the shelf life, but this variation should not be beyond or below allowed limits. Okay? Should not be below the allowed limits. So why do we need to prove stability of any produced pharmaceutical product? Because this stability study that we will perform will provide an evidence of how the quality of a drug substance or drug product varies with time under the influence of a variety of environmental factors such as temperature, humidity, and light. So the routine is to conduct stability study and to characterize the pharmaceutical product, to check the physical properties, chemical assay, and then microbiological properties, whether sterility test for sterile products, microbial count for non-sterile products. We do this test repeatedly at different time intervals while the product is stored at specified conditions of temperature, humidity, and light. And then by this way, we can find out the trend for change in these properties with time. Based on this, we can establish a shelf life. So for example, say that the limit for the drug assay should not be less than 90%. So the shelf life is the time period at which the assay of the product is between 100% at the time produced till it will reach 90%. Beyond this, it cannot be used. Okay? So when we follow the stability of APIs, active pharmaceutical ingredients, then we are talking about retest period. We will know by the rate of degradation. Then if it is stored for a while in pharmaceutical companies, they may buy bulk amounts. They will use some of it in production of certain batches, and then some may be remain stored. So for how long it can be stored and can be reused. And then when do we need to do retest and then check the degradation products and the assay and see whether this one is still suitable for production or no. Okay? And then can estimate, as we mentioned, the shelf life for the drug product and can also find the recommended storage conditions. Okay? So if the drug is degraded at room temperature quickly, then it may need to be kept in the fridge, for example. Then we will conduct the stability study at the fridge temperature, and then the shelf life recommended will be with the condition that the product is stored at low temperature. Okay, so why do we need to check the change in these properties over time? Because they affect the efficacy and safety of the final product. So when it comes to the efficacy, when the physical properties change in the pharmaceutical formulation, like particle size in the suspension, may affect, for example, bioavailability of the drug once taken orally. Physical properties like this solution from tablets, if changed with time, then it will affect also the bioavailability. When we talk about chemical assay, then once the chemical assay result decrease, means the content of the drug decrease in the dosage form, then the efficacy definitely decrease. When we talk about safety, we talk about, for example, the degradation products. Some of them may be toxic. So if they increase beyond certain limit, they may cause harm to the patient. Okay, so the shelf life is the one that during which the concentration and of the content of the active pharmaceutical ingredient should be within effective limits. Degradation products, harmful ones especially, should be within also certain limits that are not harmful. And the performance also of the dosage form, like this solution, for example, or drug release, should be also adequate. Okay. Stability study can be done on drug substance, the API, active pharmaceutical ingredient, or can be done on the drug product like tablet, capsule, and so on. Okay, so the manufacturer of drug substance, they do stability study for their drug substances, and then they check their shelf life, and they can estimate their shelf life in this way, and the suitable storage conditions also. And then it can be performed also for drug products that are finished products already, like tablets, capsules, suspensions, solutions, and so on. This is and usually should be done on the dosage form in the final immediate packaging intended for marketing. Okay, so when we talk about immediate packaging, means the packaging that comes in contact with the dosage form. For example, if you have syrup will be in a bottle, and this bottle will be in a carton box. Okay, so when you describe the bottle, this is the package that comes in contact with the syrup. We call it immediate packaging or primary packaging. But when we talk about the carton box, it is described as secondary packaging. When you perform the stability study on the drug products, on finished products, then it should be packed in the immediate packaging. It means that at least you should store the syrup packed in the bottles, that it will be also packed in when it goes to the market. Okay, there should be documentation for the results of the study. So these are the characteristics that we mentioned about when it comes to stability: chemical stability, physical stability, microbiological stability, therapeutic stability, and toxicological stability. Chemical stability, when we talk about the content of the active ingredient, it should retain chemical integrity and labeled potency within the specified limits. When we say labeled potency, means once you read on the label of the product box, it's written that this drug, each tablet contains 5 milligram. Okay, so it should retain this amount, 5 milligram. As we mentioned, there are acceptable limits, so it should vary between 100 and 90%. Can be plus or minus 10%. So usually, for most of the products, if you calculate 10% of 5 milligram, then it is how much? If you calculate 10% of 5 milligram, then it is 0.5, right? So usually they allow content variation from 5.5 to 4.5 milligram. Below 4.5 is not allowed. So once we calculate the shelf life, we calculate the time it will take for the concentration will take to decrease up till 4.5. Okay, this is what we call specified limits, plus or minus how much in percentage. Okay, Physical is the original physical properties, including the appearance. How does it look like? The color, okay? Palatability, the taste, uniformity. For example, you have solution. It doesn't change to suspension, for example. Content uniformity is when we also measure the content in several dosage form units. So you take, for example, 10 capsules, you determine the concentration of the product in each capsule separately, and then you calculate the standard deviation, the relative standard deviation of the content between these capsules to see if there is big variability or no. If no big variability, then there is uniformity in content. Uniformity is sometimes also in the same mix, okay? The solution should be stable also. The solution of, say, for example, you have a solid dosage form, like tablet or capsule. You know the dissolution test that we put one tablet in the solution medium, say, for example, phosphate buffer, and then we see the rate of dissolution of the drug or rate of release of the drug from the tablet into the dissolution medium. This is one of the tests that we perform at repeated intervals during the storage of the medication, and we want to check that this solution is not changed. Because if there is change in the solution, for example, reduction in the solution rate, this means that the drugs will have different performance. The product will have different performance. If it's supposed to act rapidly, it will not act rapidly because the release takes time. So it will be absorbed slowly, and then it will reach the blood slowly. Then the effect will be not rapid. Okay. For example, suspendability. Suspension is not supposed to be to form a cake. Usually suspensions will be prepared with some thickening agents that will reduce the speed of precipitation. So once you shake the suspension before administration, then you can take homogeneous or you can take the accurate dose, because the drug will be distributed homogeneously in the mixture. But after you leave it for some time, then what will happen is that this drug is going to precipitate, right? So you have a suspension. Suppose that particles are distributed after shaking. If you leave for some time, then it may precipitate at the bottom and form what we call a cake. Okay? So by default, the design of the dosage form is to make it not a suitable medium to make such cakes that make hard or solid precipitate that will not be resuspended again. These particles should be loose enough that once you shake again, they will be resuspended. Okay, so then this is one of the physical characteristics that the suspensions must retain. Microbiological stability means that there will be sterility or resistance to microbial growth. It is retained according to the specified requirements. So based on your product, it is sterile or non-sterile. So for sterile dosage forms, we are talking about sterility should be maintained. Sterility means that when you make a culture, you have zero growth, no bacteria at all. But then for non-sterile dosage forms like tablet, like capsule intended for oral administration, for example, like creams intended to be administered to the skin, okay, or non-parenteral dosage forms, usually requirement is resistance to microbial growth. The requirement is not to be sterile, but there should be a limit. You may get some microbial growth, but should be non-pathogenic bacteria and with certain limits. The number of colonies should not be above allowable limits. So we should check also that with storage, this microbial content did not increase. Okay. Many medications may have preservatives, okay, antimicrobial agents, antifungal and antibacterial that work as preservatives. And these are chemicals also that will degrade during the storage time. So we should add enough amount that will keep the concentration of preservative above the effective concentration till the end of the shelf life. Okay, so means that you have to calculate the rate of degradation of the preservative. If the preservative will lose about 10%, for example, during shelf life, then you have to use 110% of the required amount of the preservative. So by the end of shelf life, you have 100% of the preservative remaining, so still effective and will prevent the microbial growth. Okay. So stability in chemical stability, physical stability, and microbiological stabilities, these are the things that we always test. Therapeutic and toxicological, we don't test as a part of shelf life study, but keeping the chemical, physical, and microbiological properties stable, this will result in therapeutic and toxicological stability. Okay, so by keeping the performance of the dosage form, the content of API stable, and there is no increase in toxic degradation products beyond limit, then it will be effective. So therapeutically remains unchanged, and it will be also non-toxic. So no significant increase in toxicity will occur during the shelf life. Okay. Let's talk a little about physical stability and give some examples, more detailed examples. Physical instabilities may include, for example, crystal formation, and they may have different forms or different causes as well. Some crystal formation is, for example, during for drugs that have polymorphism phenomena. So chloramphenicol, as an example, may be produced or used in the dosage form as an amorphous form, means it doesn't have crystalline structure, but then with time it may convert to crystalline form. Saturated solutions also may have during storage, once the temperature varies, then solubility also varies, right? So then it may have some precipitation of the solute, and then it will form crystals as a precipitate. There will be some crystal growth. In suspensions also, there is phenomenon, we call it Ostwald ripening. We may make a small suspension with fine particles, and then with the changes in temperature also during storage, there may be some fine particles will dissolve, and then some small crystals will, the larger crystals will grow, and then there will be a change in the size distribution between the crystals, between the particles. So we may have growth, and then we will have larger particles in the suspension. Larger particles in the suspension is not good, because it means the precipitation is higher, there may be some caking, and upon administration also the solution will be slower upon ingestion. Okay. Some physical changes also may have the form of loss of volatile substances from pharmaceutical dosage forms that contain volatile substances. So for example, aromatic waters, they have volatile substances dissolved in water. So this aromatic ingredient, aromatic means volatile, and have characteristic aroma or smell, they will evaporate. So there is loss of the content. Elixirs, they are hydroalcoholic solutions. So alcohol may, and the drug usually used for drugs that not soluble in water. So to dissolve them, we make mixture of water and alcohol. So this alcohol may evaporate, and once evaporate, solubility of the drug decrease, and then it may precipitate. Spirits, they are also hydroalcoholic solutions, especially of volatile substances. There may be also some evaporation of volatile substances from them. We have a drug called nitroglycerin. Nitroglycerin is used for angina pectoris. It is a heart condition characterized by low blood supply in the coronary arteries. So it will cause ischemia to the heart. Nitroglycerin by nature is a volatile substance, and it is available in the pharmacy as in the form of tablets. So to be taken sublingually, can be taken sublingually, so that they produce rapid effect. So once the patient feels pain in the heart, there is ischemia, he will take this drug to dilate the blood vessels. He just place it under the tongue, it will dissolve quickly. So nitroglycerin, because a volatile substance, upon storage, can evaporate. Okay, can evaporate. So aromatic substance or volatile substance, you can say instead of aromatic water. Some types of tablets which contain volatile substances like nitroglycerin in tablets, they may also show less content with time due to evaporation of the active ingredient. Some dosage forms, the physical change will be loss of water. This can be seen, for example, in saturated solutions. They will start to lose water and then become, in this case, will become supersaturated. So the precipitation will start to occur and we will see it as the formation of crystals. Emulsions also is a dosage form containing oil emulsified in water. This water loss with storage may lead to separation of two phases and change to, or sometimes phase inversion we call it, changing to the other type. Means you have, for example, oil and water. Usually the dispersion will be, if you want to make, for example, if you want to make oil in water emulsion, then the amount of water should be more than oil. Okay, so if you have loss of water with time, then what will happen? If the oil become more than water, then you may have inversion, means that it will be water in oil emulsion. Oil and water emulsion means that you have a medium. And you have oil globules in water medium, right? So the medium is, the globule is oil. The medium is water. But once inverted means that the globules are water and the medium is oil. Okay. Creams also, as you know, creams are emulsions. They may be oil and water or water and oil emulsion. So especially oil and water creams means because water is the external phase, so it is exposed to loss and creams will become dry. Pastes also contain some water content. They may become dry. Ointments, especially ointments may be hydrophilic, may be hydrophobic bases. Hydrophobic bases are waxy materials. No water, doesn't have any change. But if they are aqueous or hydrophilic bases in the cream, then there will be loss of water and dryness. So how to prevent this loss of water? Usually in the formulation, we include a substance called humectant. And this humectant is a substance that can absorb water. Okay, so it will keep the water content in the formulation. So humectant is added to these dosage forms and it will absorb water from the atmosphere and prevent drying or loss of water from the dosage forms, such as glycerin. Glycerin is one example of the humectants that are added to the dosage forms to keep its water content without change during storage. Contrary to this, some dosage forms may absorb water, and it can be seen especially in dry substances like powders, or for example, liquefaction and degradation may occur as a result of absorption of water. So especially if you have a moisture sensitive drug in your formulation, then tablet dosage form or powder, whatever the dosage form, absorption of water may lead to degradation of the active pharmaceutical ingredient in this dosage form. And suppositories, for example, which have substances like glycerin, gelatin, or polyethylene glycol, they all have the ability to absorb water, so their consistency will change with time because they absorb water, they become softer, so they will give a jelly-like appearance instead of being harder. Okay. How to prevent this? You cannot change the characteristic of the material, but it's through packaging. You can pack in packaging the material that is impermeable to water. Okay, so it will prevent entrance of water to the dosage form. Okay, so how to prevent? You prevent this one through packaging. Okay, through packaging in water resistant containers. Okay, water impermeable containers. Change in crystalline form may happen. For example, cocoa butter, as we know, used in suppositories. This one have polymorphism phenomena or have polymorphism characteristic. So this one, upon storage, it may, if you store at, for example, freezing temperature, then the crystalline form will change. It will give change to different polymorph with different melting point. Okay, so it will affect its melting in the body once inserted. It's used in suppositories. Chemical instability, as we mentioned in the previous lecture briefly, that it may appear as you have drug usually, and this drug will be converted to degradation products. Drug or API will give degradation products, right? So your drug is effective. The drug is responsible for effect. And these degradation products may be, not all of them, may be toxic. Okay? So the chemical instability may result in loss of potency when the drug amount decrease and will result in accumulation of toxic degradation products if the degradation products are toxic, right? So here the shelf life can be estimated based on both reduction of effect and increase of the limit of the degradation product to the toxic limit. So which one will rely on? We'll rely on the one that comes first. Means that if, for example, the limit for drug product is 90%, and it can reach to 90% from 100% to 90% in 4 years, but the degradation products can reach toxic limit in 2 years, then which shelf life you will take? Definitely the shelf life of the product will be the 2 years, not the 4 years. Okay? Degradation not only happens to the API, but even it can happen to excipients and affect the formulation. For example, emulsifying agent may degrade with time. So then emulsification property will be lost. Then you'll have separation of your emulsion phases. Instead of oil, for example, emulsified in water, they will be 2 separate layers, oil separate from water. You also have preservatives in your formulation to prevent microbial growth. Then if the preservative degrades below the effective limit, then what will happen? You will start to observe microbial growth in your product. Okay, so the product microbial characteristics change and cannot be used, right? So you have to be sure that you account for the degraded amount of these functional excipients during the storage time, so that you keep the performance of the product, you keep its physical and microbial characteristics stable. Okay. There may be some color change, for example, like what we see in adrenaline. Even there is little change in the content, but it gives different color, which is not acceptable by physicians, pharmacists, and nurses. So usually adrenaline expiry date will be based on the change on physical property. Even the content did not change too much. Okay. Microbiological stability, as we mentioned, the change in sterility or microbial growth in the product. There are different sources that may cause microbial contamination of the dosage form or the pharmaceutical product, including water that will be used in the formulation, like for example in syrups or suspensions, the air in the environment surrounding the product, whether during production or handling or storage, raw materials or after opening the product package for use. may come with the raw materials, with the containers and closures that we pack the product in. It may come from the personnel, the people or the staff that are working in the manufacturing plant and handling the medication. It may come from the instruments and the apparatus used for production of the dosage forms. Okay? So what factors that will affect the rate of reaction, which is drug degradation or drug stability here? Many factors may affect the drug stability by affecting the rate of degradation of the drug product. Temperature, pH, of the pH of temperature of the storage in the storage place, okay? And then pH is the pH of the medium of the pharmaceutical product itself. Light, if there is light that comes in contact with the product, moisture around the product, ionic strength of the product itself, dielectric constants of the solvents used if you have a liquid dosage form like solution or suspension, any catalysis by any agent that may speed up the reaction in the medium, presence of surfactants, and pharmaceutical dosage form type itself, whether it is solid or liquid dosage form. We will talk about them one by one. First, temperature. Usually, the higher the temperature, the higher the rate of degradation of the product, whether the degradation is due to oxidation reaction, reduction reaction, or hydrolysis reaction. So higher temperature means faster drug degradation. That's why for drugs that degrade at room temperature, we just keep them in the fridge, and the recommended storage temperature is about 4 degrees. Why? Because at low temperature, they will have very low rate of degradation, so they will have a longer shelf life. Okay? Rate of most chemical reactions increase with the rise in temperature, up to 2 to 3 times with each 10 degrees rise in temperature. So if you store it at, for example, 20 degrees, and then there is a certain rate of degradation, you increase by 10 degrees to 30 degrees, you store your medicine at 30 degrees, then rate of degradation will be maybe twice or 3 times. So shelf life will be reduced into half or reduced into 1/3, right? So the shelf life will be reduced into half or reduced into 1/3. There is a relationship that gives you the rate of degradation, how to calculate. We call it Arrhenius equation. Arrhenius equation, you have here the temperature. So rate of degradation increase as the temperature increase. Okay. These are constants, constant activation energy. Okay. But in general, if you look for the relationship between degradation rate and the temperature, you will find that with increase in temperature, there should be an increase in the reaction rate. Okay. If you take log or ln value, some forms in some textbooks, you'll find it ln. You'll take ln of both sides, then the equation will be converted to ln K equal to ln A minus A divided by activation energy EA divided by RT. Or as we mentioned before, if it is log form, the mathematical relation or conversion factor between log and ln is 2.303. So if it is log, you have 2.303. Okay? Why? Because the original form that we use in studies always is ln. So if we use log, then it means converted from ln. Then there will be a conversion factor 2.303. Okay? This is why you have 2.303 here. K is the reaction rate, as we mentioned. A is a constant. We call it frequency factor. EA is the activation energy of activation. R is the gas constant. It is constant value, 1.987 calories, degree to the power -1, mole to the power -1. Or in joule per mole, it is 8.314. T here is the absolute temperature. How much is the temperature of storage? Then you put the value as it is in Celsius, degree Celsius. Okay. Now we look for this equation as a linear equation. Y equal to intercept plus slope times x. Okay, so here what is the slope, what is x? K is y and 1 over t is x, and the slope is activation energy divided by R times 2.303. If it is ln K versus 1 over T, then you don't have this constant 2.303. Okay? So if you do store your product at different temperatures, and then you measure the content at time 0 and, for example, after 3 months, and then you see how much was the loss, you divide by 3 months, and then you calculate the degradation rate per day, per hour, whatever the unit you use. You can plot it against 1 over t. This will give a straight line, as you mentioned, and the slope is this value, and the intercept is log a. Okay, so in this case, by extrapolation, you can find out how much is the K at other temperatures that you didn't experimentally study. Okay, for a reaction carried out at 2 different temperatures means you didn't study at so many temperatures that you make a plot from 3 points or above. You may study at 2 different temperatures only, then the equation will be like this: log that you minus the temperatures, the 2 equations. So you will get log K2 divided by K1 equal to activation energy divided by R times 2.303 times the difference in temperatures divided by multiplication of the temperatures. T1 is the storage temperature 1, K1 is the degradation rate or reaction rate at temperature 1, K2 is the degradation rate at temperature 2. Okay, for example, you store the product at temperature 50 and 60, then you determine the degradation rate over 3 months period, for example, or 1 month period at 50 and at 60 degrees. You calculate the K1, K2, and then you already know T1 and T2, the storage temperature. Then from this you can find out the ratio between EA and R. R is constant. We give the value already, so you can determine the activation energy of your drug. Okay. One of the factors also is photodegradation, means once, of course, not all drugs are light sensitive. Some drugs are light sensitive, so this we have to determine during our stability study. We will expose the drug to light, and then we see whether it degrades with light or light doesn't change the degradation rate. How to know? You have 2 samples, one exposed to light and one just stored at normal temperature, same temperature, but no exposure to light. And then you see whether, means you pack it in some packaging that doesn't allow transmittance of light. And then you measure the degradation rate in both. If degradation rate is faster in the one exposed to light, then there is photodegradation that happens to your drug. If it is significant, you have to protect your drug from light when you store it. So the packaging must be light resistant or doesn't allow transmittance of light. How light can cause degradation? It may provide activation required for the light energy itself may provide activation required for the degradation reactions to occur, whether it is oxidation, reduction, whatever, as we mentioned before, or hydrolysis, it will activate the reaction. And then upon absorption of radiation and energy, this will activate the molecules independent of temperature for activation of the molecules. Okay, absorption of one quantum of energy increase molecules kinetic energy. They will have higher kinetic energy, move faster, more collisions between the molecules, means that more chance for them to react, and this will be followed even by temperature rise. Okay, so you have to control wavelength and intensity of light and the number of photons absorbed by the material. How to control this? If your drug is known to be photosensitive, then you have to pack it in amber bottles or opaque containers, dark containers that doesn't allow light to pass. That's the reason why you buy some medicines. you find that they are packed in a transparent bottle, and some medicines are packed in amber color bottle. You buy some tablets, they are in transparent blister pack, just covered with that have the other side aluminum foil, one side is transparent plastic. And sometimes you buy medication tablets in the form of tablets, and then you find that the plastic part is dark color. Okay, why we use dark color means that this drug is photosensitive. If we didn't use dark color, means the drug is not degraded by light and it doesn't affect its stability. Okay, the solvent in liquid dosage forms also have effect on drug stability. Drugs unstable in aqueous solutions may require incorporation of water miscible solvent with as low molecular weight alcohols. Okay, so if you have a drug that usually water is the cheapest solvent, universal solvents commonly used. So if your drug stability is okay in water, we have no problem. If not stable in water, in aqueous solutions, then you may modify the solvent. You can make a mix of water with water miscible solvent like polyethylene glycols, propylene glycol, and so on. They may stabilize the drug. Okay, how they stabilize the drug? By altering the activity coefficients of reactant molecules and transition state. They change the physicochemical parameters like the pKa and viscosity of the medium, so they affect the reaction rate directly. Less polar solvents in general will slow the reaction, while more polar substances will speed a reaction. Usually because this one depends on the degradation product itself. If the degradation product is more polar, then polar solvent will increase the speed of the reaction. And usually degradation products are more polar. They are more water soluble compared to the original product. Okay. Dielectric constant of the solvent also is important aspect. So we have to consider once we develop new drug preparations. It can influence the rate of reaction, the degradation reaction. It depends on this reaction. Does it occur between more ions of opposite charge, opposite sign, or same charge? Opposite charge means inverse relationship, means that increase in dielectric constant decrease the rate constant. You remember it in this way: opposite sign, opposite relationship, or inverse relationship. Same sign, then if ions, reacting ions that will cause form degradation product at the end, they have the same charge, then it is direct relationship, means increase in dielectric constant of the solvent results in increase in the rate of reaction. Okay. There may be catalysis that may happen, some conditions. Like for example, we have specific there are different types of catalysts. So first we define what is catalyst. Catalyst is substance that will speed up the reaction. Means the degradation product is at slow rate in absence of catalyst. Once you add the catalyst, usually it will increase the reaction rate. If we just say catalyst, we don't say negative catalyst, so we mean that it will increase the reaction rate. Okay? In general, it influences the speed of a reaction without itself being altered chemically. Its chemical structure will not be changed. And in general, when we just say catalyst, then we mean that it increased the reaction rate. Okay? But when you say negative catalyst, that means that this substance is inhibitor for the reaction. Once you add it, it will inhibit the reaction. So it will stabilize the drug in this case. Okay? How do they increase the reaction rate? They lower the activation energy, which is the minimum energy required for the reaction to occur. Okay? As a property of catalyst, they don't change the equilibrium of the reaction. Means that if the equilibrium means reaction stops by having 70% in the medium as degradation product and 30% as reactants, or the drug itself, API, this means that Even you use a catalyst also, the equilibrium is same, 30-70, no change. But the change only in the time to reach this equilibrium will be shorter. So you speed up the reaction. Okay? They may operate in several ways. They may combine with substrate and form a complex. This complex decomposes to regenerate the catalyst and yield the product. So the catalyst will be released again and no change in its chemistry, and then the products will result. This catalyst usually decreases the energy of activation by changing the mechanism of the reaction process. Or some catalysts, by other way, they produce free radicals like CH3 radical, which causes fast chain reactions. Chain reactions means that several steps will proceed till we've reached the final product. So chain reactions, they are reactions consisting of series of steps involving free atoms, radicals that act as intermediates, and there is initiating step, and there will be so many intermediates will be formed intermediate. For example, compound 2 will be converted to compound 3 to compound 4. At the end, it will give the final product. This final step is called terminating step. Okay. Catalytic action, the catalyst itself or catalytic action may be homogeneous or heterogeneous, may occur in either the gaseous or liquid state. It can occur in different physical states. If the catalyst is same physical state like the other reactants, we call this homogeneous catalysis. Okay. So, for example, you mix liquids, all of them are liquids. Catalyst is liquid and or dissolved in the medium, and then all your drugs, your substances that interact with each other are dissolved in the medium. This we call it homogeneous catalysis. But for example, some reactions like you use metal catalyst, for example, like nickel. You have it you studied it in organic chemistry, some reactions. Nickel, for example, for the hydrogenation of oils, we use nickel as catalyst to produce the margarine. So here, this is heterogeneous catalysts. Your reactants are liquids, but your catalyst is a solid metal. Okay, in the solid phase. Others are liquid phase. This we call it. Then we call it heterogeneous catalysis. Okay. Specific acid-base catalysis. This means that the catalyst will work only in acidic medium or basic medium. Okay. So here, addition of acids or bases will accelerate the drug compositions. No rule. It's different from drug to another. Some drugs will be degraded faster in basic medium. Some drugs will be degraded faster in acidic medium. Okay, so here accelerated decomposition is found to contain a term involving the concentration of hydroxyl ions. Okay, they affect the or they speed up the rate of degradation. So hydrolysis, especially, there is acidic hydrolysis and there is alkaline hydrolysis. Okay. So the hydrogen ion concentration indicates that the process is a specific hydrogen ion catalyzed reaction. If we said specific acid catalysis, then there must be hydrogen ions. Okay, but if you say general acid catalysis, then any acid, any proton, positive proton can accelerate. Okay. So if you know that your drug, for example, can degrade in acidic medium, then you have to keep the pH alkaline, for example, to make it stable. So how to control the pH of the medium and vice versa? Degraded in alkaline medium, you have to maybe keep your your medium pH slightly acidic. How to control the pH of the medium? You may use buffer in the formulation. So buffers are used to maintain the solution at a particular pH. So the composition of the buffer will determine how much is the pH of the medium. And then this buffer will maintain the pH stable. Acidic and alkaline pH influence the rate of decomposition of most drugs, as we mentioned. Many drugs are stable at the pH of 4 to 8. Sometimes we change the pH to increase the solubility. So by changing the ionization of the drug. So for example, weakly acidic drug If it is not water soluble, we want to increase water solubility. We want to make it ionized. We put it in basic medium. Basic drug, we put it in acidic pH. Then it will be more will be ionized. So we'll improve the solubility here when they are ionized. But the problem that when you adjust the pH to increase solubility, then through the pH change, then the drug will decompose faster compared to non-ionized one. Okay. So if you find that your drug, you want to increase the solubility of the drug, better not to use the pH control for increasing solubility, because it will also increase degradation of the product. What is the alternative? You can use co-solvents. Co-solvents, as we mentioned in the previous slide, water miscible solvents that we will mix with water. They mix with water. Once you mix them, they will not form a separate phase, but they will be only one liquid phase. And this can increase the solubility of water insoluble products. We said, as an example, propylene glycol or alcohol, ethanol can be mixed with water. And they increase the stability at the same time by suppressing ionization, reduce the extreme pH required to achieve solubility. You don't need to change pHs drastically to increase solubility. Enhance the solubility of the product without increasing its ionization. And also at the same time, they reduce water activity by reducing the polarity of the solvent. For example, you put 20% propylene glycol in chloride diazoxide injection for this purpose, then it will solubilize chloride diazoxide. It also affects the dielectric constant of the solvent and increase stability. Okay, so in stability studies, we may store the drug at different pHs, and then we keep temperature, ionic strength, solvent concentration all constant. We just change the pH. We can store the drug at different pHs and then analyze the content, determine the content of the drug at the beginning and at the end, and calculate the rate of degradation, and then find the most suitable pH for storage of the drug. The pH that gives the least degradation rate is the suitable pH for storage. Okay. Some buffers, then how to maintain this pH? By the use of buffers, as we mentioned. There are different types of buffers. Each one is suitable for different pH range. So it depends on the pH that we need to achieve. Then what is the buffer that have better efficiency at this pH, and then we use it. You can use acetate buffer, citrate buffer, lactate, phosphate, and ascorbates as examples. They are utilized to maintain the pH of the formulation. Okay. Sometimes only a change in one unit of the pH can change the degradation rate tenfold. Okay. So when we are formulating a drug into a solution, we should carefully prepare a pH decomposition profile. Means that we study what is the rate of the change in the rate of decomposition with the change in the pH. And then we formulate the drug. We adjust the pH of the formulation to the pH that will result in the least or slowest degradation rate of the drug. Some other factors that may also increase degradation of products: moisture, oxygen, the type of pharmaceutical dosage form, and incompatibility between the ingredients of the formulation. Some drugs are, not all, some drugs are moisture sensitive. Usually water catalyzes chemical reactions as oxidation, hydrolysis, and reduction reactions, and usually there will be hydrolysis reaction once there is increase in water content, and also increase of water content in the formulation will promote microbial growth. The more dry formulation has less growth. So in liquid formulations we use preservatives usually, but in dry formulations like tablet dosage form, capsule dosage form, the most important is to keep them dry. You don't need usually to use preservative in them. Okay, so during your stability study, if you find that your drug is moisture sensitive, then how to control moisture? Again, by the packaging. So you can use water impermeable type of packaging that will not allow environmental moisture from air to enter into the dosage form package. Some drugs are very sensitive to oxygen. They may be oxidized and then stability will be affected. and even this one can be overcome by gas impermeable packaging material, and same time also even some injections. There will be inert gas like carbon dioxide or nitrogen that will be in the space above the formulation inside the package. Pharmaceutical dosage forms, also the type of pharmaceutical dosage form affects stability. In general, liquid dosage forms are less stable than solid dosage forms. Okay, due to the presence of water, there will be hydrolysis reactions mainly. So it is preferable to make as much as you can in solid dosage form. If your drug you may need to make injection, you need to make syrup, for example, then it will be in liquid dosage form. If it is stable enough to have a good shelf life, like 2 years or more, then can be produced. If the degradation rate is fast and you cannot have this kind of shelf life, then the other way is like what you see in some antibiotics. They are prepared as dry mix, so it is solid dosage forms initially, that is kept on the shelf as a solid dosage form, so it will be more stable. You just reconstitute, you add water before the use, you dissolve or suspend the contents, and you should not use within long period. Usually should be used within at least 2 weeks to 1 month period, because there will be a faster degradation rate. After this short period, the concentration of API will decrease. Okay, drug incompatibility. As you know, any dosage form is composed of drug plus excipients, and you may have even more than one drug in the same. You may have more than one drug in the same formulation, right? So you should be sure that these are compatible with each other. Drug incompatibility means the drug has the ability or liability to interact with the excipient. So this will be in the formulation development at the beginning. We have to try different blends, the drug with different excipients separately. So we make formulation 1, for example, formulation 2, formulation 3. This one have drug plus excipient A. This one have drug plus excipient B. The formulation 2 have drug, for example, plus excipient C. Okay, and then we study their stability. We observe the stability over time, and the one that has the shortest, the slowest degradation rate is the suitable blend or suitable formulation. Okay, there are many experimental methods to check for the compatibility between drug and the excipient. Compatible means they don't react. Incompatible means they react with each other, so they cause degradation of each other. This also incompatibility may be between the drug and the package. Maybe between the drug and the package, not only drug and excipient. This is an example also of drugs that are degraded by some factors, like acid catalyzed hydrolysis of digoxin. It follows pseudo first order reaction kinetics. So we mentioned last time what's the meaning of pseudo first order. Means the reaction itself is not a first order reaction, but maybe due to excess of one ingredient, one reactant compared to the other, it will go in the first order rate. When you measure, you plot the concentration versus time, you get a mathematical or the equation of first order reactions. Here the concentration of hydrogen proton remains constant, therefore the rate slowly depends on the concentration of digoxin. It is acid hydrolysis. There is interaction with the proton, but proton is in excess, remaining constant, so the rate depends on one factor, the change in concentration of digoxin. Okay, hydrolysis of chlorbutanol in presence of sodium hydroxide also follows a second order reaction. So these are examples. We stop by expiry date. The next hour we can discuss the expiry date. Can we have a 5 minutes break and then we resume? Okay, so back to the expiry date. This is the why do we need to study stability? So stability is that we mainly measure two things: the change in physical properties and physical, microbiological, and chemical properties with time during storage at controlled conditions. And then based on this one, we can find out the suitable temperature and the time during which the product is stable enough. Not, of course, will not be stable completely, but stable enough means still have the required characteristics or allowed variation in chemical, physical, and microbiological characteristics. Okay, so this period we call it shelf life. We call it shelf life. So your product shelf life, as explained before, is 2 years. Then based on this, you can write on the box what is the expiry date. So expiry date will be 2 years after the production date. So always you have two dates: production date and expiry date. Produced, for example, in 2020 and then will be expired in 2024. From 20 to 24, the 4 years is the shelf life of your product. Okay. This expiry date or end of shelf life means that the drug cannot be used after this date because the concentration of the drug is decreased and become lower than therapeutic concentration. And as we mentioned in the previous slides, it's not only depending on the decrease in drug content, but also depends on the increase in the content of toxic degradation products. Okay, and also physical characteristics like that will affect the performance of dosage form, like the solution and so on. They must be stable also. They must not change significantly on storage. Okay. This expiry date or shelf life applies when you store at the recommended conditions and your package is still closed. You didn't open the container yet. But after opening the drug container, expiry date will change, will be shorter, as a result of decreased concentration of the drug or the result or as a result of the risk of contamination. So for example, eye drops, usually they recommend maybe the shelf life is still, there are 2 years remaining, but once you open the eye drops and you use it, the recommendation is to use it for 1 month maximum after opening the dropper, not longer than this. And this is usually not because of the risk of degradation, but mainly because of the risk of contamination, microbial contamination. As you know, eye drops are sterile dosage forms, and eye is a very sensitive organ, and you will not allow the use of eye drops for longer duration after you open it. Even the shelf life or the expiry date on the box stating that it is still suitable for use. Okay, so here mostly because of risk of contamination. Syrups and suspensions of antibiotics that are prepared as dry mix, as we mentioned, because they are unstable in the aqueous solvent as solution, they are not stable, so we prepare them as dry mix, and then you add water and then you mix, then you make from this syrup or suspension. Okay, depends on the nature of the blend itself or the mixture itself. Once you add water, then the rate of degradation will become faster, and it's not really suitable for use for a long time. So it can be used for 1 week by storage in room temperature, and 2 weeks if you put in the fridge. At 4 degrees means you put in the fridge. The degree in the lower compartment of the fridge is 4 degrees. In the freezer it is -20. Okay, so we say 4 means we put in the fridge. Okay, so if you have a patient and then you dispense for him syrup or suspension that is in the form of dry mix and you need to reconstitute, then you advise them to keep it in the fridge and not to use it after 2 weeks period. Within 2 weeks he must consume the dose. Means if any remaining from the dose, he should not use it if more than 2 weeks passed. Okay. For tablets and capsules, they remain stable in the package, but after removal, the expiry date will change because they will be exposed to moisture and light and the air also. there may be some contamination, okay? Moisture and light may cause accelerated degradation. Ampoules is a sterile dosage form. Once you open, you should use immediately. You cannot keep for a long time, okay, if it is single dose ampoule, but multi-dose vials are stable for longer time because there is preservative in them. Not only 24 hours. For example, insulin can be used over a 1 month period, okay? So just don't take this 24 hours sharp. Okay, because patients with diabetes, they use insulin, they will keep taking dose from the same vial for up to 1 month. It is okay. There is preservative in the dosage form. Now we go to experimentally, how do we determine the shelf life? How do we do this? Through stability studies or stability testing. And there are 3 types of stability testing. As we mentioned before, in Arrhenius equation, the reaction degradation rate is proportional to the temperature. The higher the temperature, the higher the degradation rate. So if we want to see fast results, if we want to see what is the degradation profile of this product, what substance it will produce, so I want the reaction to go fast, then I store at higher temperature. This is what we call it stress testing. It is called forced degradation study. I force the degradation, I accelerate the degradation by storing at aggressive temperatures, 50, 60, 70 degrees. It is just predictive in nature, not definitive, because reactions that occur at higher temperature may not occur at low temperature. Okay, why it is predictive, not definitive? Because not all the reactions that occur at higher temperatures will occur at low temperature. So maybe you have some estimation at high temperature, but once you store at the normal room temperature, you will not get the same results, because some of the reactions that will occur at 60 degrees may not occur at 25 or 30 degrees. Okay, the objective is to discover potential stability issues with drug molecule, predict drug excipient compatibility. So I will store the drug alone, the drug with the excipient. I see the difference in the rate of degradation. If I have a faster rate of degradation in the drug excipient mix, this means the excipient accelerate the degradation of the product, right? It can provide scientific foundation for developing stability indicating analytical method. Okay, now I need to develop an analytical method to determine the content of if you want to determine the content, you need to have to develop analytical method suitable to determine the content. Okay, should be stability, we call it stability indicating method. What does it mean, stability indicating methods? Means that it can determine your product in a complex mixture, that with the product you have different degradation products. So now I want to test if the result will change by having degradation products in the medium or no. How can I make this? I need to prepare a sample with a lot of degradation products. So in this case, I will force the degradation of the drug by including in by storing at high temperature, by using acid or base forced degradation, okay, alkaline hydrolysis, acidic hydrolysis. I can use oxidizing agent and so on. So I will use these samples for testing or validation of the stability indicating analytical method. Okay, and also by speeding up the degradation, I can produce more degradation products, separate them, identify them. So it can help to identify the likely degradation products of drug substance and try to find the degradation pathways, means the type of reactions that will cause the formation of these drug degradation products. Okay, so I can do stress testing for both, for formulation and for the API. So the API manufacturer can study the API itself, the drug alone, the pure drug. So can do stress testing for it. Once you study the degradation, you have to use discriminating methods. This is the same as we say stability indicating method. Okay, you have to use stability indicating methods, means that this method can determine the drug in presence of degradation product. Of course, you cannot use a method like spectrophotometry, but you can use HPLC. And in HPLC, the chromatogram and the conditions must be able to separate the peak of the API from the peaks of degradation products. In this case, you can determine it exactly. Okay. So you identify the potential degradation products, and pathways means the types of reactions that lead to this degradation. You can do it for the formulation also. Use information from stress testing to aid in the development. As I mentioned to you, that you can, in your mind, you can use different types of excipients. You have several excipients that can be used for one function. For example, solvent, the simplest thing is solvent. You have three types of solvents that can be used. You don't know which one is more compatible that will preserve the stability of the formulation. So I prepare three different solutions, each one with different type of solvent, and I compare between them. I store at higher temperature so that the reaction will be faster, so that I can get results in a short time, like 1 month. I don't want to wait for 1 year to get the results. So I store at higher temperatures. After 1 month, I get my samples. I compare the rate of degradation between the three solvents. The solvent that gives the shorter rate of degradation is the best one. Okay, and this is an example of using it to aid the development. And to determine the content, the concentration of the drug at the beginning and after the 1 month period, I need to use a analytical method. This method should be discriminating method or stability indicating method. And this is what we call it drug excipient comparability studies. And then I can also test a trial formulation, means there is candidate formulation, final I want to test. So I don't want to wait for a long time. Maybe I can do stress testing. I see the results within 1 month. If it is impressive, then I can continue the normal procedures after this. Okay. Here also I can identify potential degradation products and pathways that are not detected in drug substance stress testing, because here is drug substance alone will degrade, but here there will be some reactions between the drug and the excipients. So you have more pathways that can be identified. If things are okay, then I go to the second stages, second and third. I can do accelerated and long-term testing. For stress testing, it is internal study. You don't need to submit this data for registration of the product, but accelerated and long-term testing are usually the data will be submitted to the registration for registration of the drug product. Accelerated testing, I just keep at high temperature than the storage one, but not that very severe temperature. This one can be used for determining significant degradation products, develop focused methods also for analysis, and identify containers and conditions to minimize the degradation. Okay, so I can also store in different containers and see the drug container or formation container compatibility. Long-term testing is we determine degradation product levels, develop specifications, and establish storage conditions and shelf life. Long-term testing used for calculation of shelf life mainly. And this is in long-term testing, we store the formulation in the primary packaging, as we mentioned, or immediate packaging, and we keep it at the storage temperature that should be stored at upon marketing. Okay, the normal temperature, either 25 or 30 degrees, or if it is heat sensitive, then usually 4 degrees. And some products can be frozen. Okay. So stress testing, as we said, we increase 10 degrees increments, 50, 60, 70 degrees, for example, and controlled humidity, usually about 75% relative humidity. And we may expose to light, okay, to check if there is photolysis that can happen to the drug. And this is done to evaluate susceptibility of the drug substance to hydrolysis across a wide range of pH values. This testing should also evaluate the effect of pH. We can also, if you have liquid dosage form, and then you can also, one of the parameters you study is the effect of pH on the stability of the drug. An accelerated stability study we increase the rate of chemical degradation or physical changes of the formulation or drug substance if we are studying drug substance, using exaggerated storage conditions as part of the formal stability studies. Here we are talking about formal stability studies. Means this one is we have the data should be controlled, documentation should be provided, and the data will be submitted with the product file when we want to register the product. So it will be examined by the authority, by registration body, National Pharmaceutical Regulatory Agency. Okay, and the data of this one we can usually they rely on this data initially to determine whether this formulation is stable or no, and they will give some preliminary shelf life, maybe 1 year at the beginning, and then if the drug shown to be stable during accelerated stability study, they will grant 1 year shelf life. But then the extension of shelf life will depend on the long-term stability study. Okay, as we mentioned, the results, why they just use or rely on it preliminary only but not finally, it's not a definitive one, because as we mentioned, accelerated testing at higher temperature usually some reactions may occur that don't occur at normal temperature. Okay, so it's can be carried out also during the development, can be done on pure drugs to assess the stability and identify degradation products and pathways or mechanisms. The good thing that why we use it, because high temperature, as we mentioned, increase the reaction rate, so you can get the results faster. So you want to shorten the development time, the drug development or formulation development time. Okay, and can be used to extrapolate or estimate the shelf life at room temperature. We will show how to extrapolate. Very often done in early stages of product development to support, as we mentioned, the establishment of product shelf life. Testing can be done at 50, 60, and even 70, but and then in humidity, usually on humid conditions, 75%. 1 month can give sufficient, is often sufficient to provide initial assessment, but for regulatory purposes, the standard method is to do it at 40 degrees only. Actually, what we explain here may be a little different from the regulatory requirements now. We will explain it in another lecture on another subject in details, but in general, if you want to follow the textbook method, just you want to calculate the reaction rate at 25 degrees or 30 degrees, the room temperature, then you need to make a plot. So you need to do this. This is more like stress testing, 50, 60, and 70 degrees. It's a kind of accelerated stability study. And then you determine K at each degree. Maybe you can follow for 1 month is enough, or 3 months maximum. This is enough to make the plot. So in this way, you will plot usually if you have first order reactions, log concentration versus time, you get linear relationship lines, different lines. As you see here, the more steeper means faster degradation. At higher temperature, degradation is faster. Lower temperature, degradation becomes slower, slower, slower. You can calculate the K, okay, from the slope of each curve. So you get the K values for the composition of the drug at different temperatures. Okay, then you make a plot for log K versus the Arrhenius equation that we mentioned before. In Arrhenius equation, log K equal to log A, we mentioned, minus E divided by R times 2.303, and then times 1 over T. So as I remember, so if you plot 1 over T, this is the X, and then log K over Y, you have the K at 70, 60, 50, and 40, right? So we mentioned before that we extrapolate. How to extrapolate? You extend the line down. So you can determine what will be the expected K at, for example, 30 degree, what is the K at 25 degree, what is the K at 20 degree. So if you are planning to store your product at 30 degrees, you have the K value. then you can determine the time the concentration will drop from 100 to 90%, as we made in the previous lecture. Okay, this is the way to extrapolate the results from accelerated stability study uh, to calculate the K, or reaction rate constant, um, at the room temperature or storage temperature, that you didn't do experimentally, because experimentally, if you want to find significant degradation, then at 30 degrees you need to store for a long time, maybe 1 year or something, to calculate. So you can do this accelerating the rate and do the study in 1 to 3 months, maximum 6 months, and then get results. Okay. For formality, nowadays this data will not be sent to regulatory bodies. They don't take anymore this for you. And as we mentioned, the extrapolated K is not always true, because maybe some reactions will occur at higher temperature, will not occur here. So the rate of degradation may be even slower. The reaction rate constant may be even smaller at room temperature. Okay. And then you have to, these are what we mentioned, that considerations when you do accelerating stability studies. The degradation rate constant is not applicable when you change the blend. When you change the formulation, then degradation rate may be different completely. The testing method you use here to assay to determine the content of the drug at different time periods, this should be stability indicating method. So you cannot use, for example, spectrophotometry, because all the materials will be in the mix, all will have absorbance, all will give results, they will interfere with each other. So you have to use a method that's, for example, HPLC, and you have to, during the development of the method, you have to prove that you have separate pure peak for the drug component, separate from the peaks of the other materials in the mixture. And some statistical analysis may be done, which is no space here to explain more about it. Methods for estimation of product shelf life. As we mentioned, shelf life in most of the products, some is only decreased by 5%, but majority is the time that the drug will assay will be decreased by 10% if we rely on the drug content for calculation. Okay. So there are mainly two methods, Q10 method and reaction order equation. These two methods can be used for prediction of shelf life. This one we used last time. This is a first order reaction equation. We have two concentrations, C0 and content after this, C at certain time, and the time between them equal to 2.303 divided by K log C0 divided by C. If we use ln C0 divided by C, then we don't need to use 2.303. So it is the same equation last time we used. The equation was or delta T equal to ln C divided by K. And K is the reaction rate constant. So if you know the reaction rate constant, you did it by plotting, by extrapolation, for example, then how much is C0 is 100% and C is 90%, right? And whatever, like this example, for example, is mentioning that the initial concentration of drug decomposing according to first order kinetics is 94 units per ml, whatever the concentration, and the specific decomposition rate obtained is 2.03 times 10 to the power minus 5. At room temperature, 25 degrees, and it shows that the allowed here not only fall 10%, fall by 50% here almost, but whatever we have initial concentration and final concentration. So the one that initial and then the least allowable concentration, 45 units. Below it, there will be no effect. So the last thing I can allow is 45. So between 94 and 45, how much the time? This is the shelf life. So I apply in the equation T is equal to 2.303 divided by the K value that is given here, log the initial divided by final concentration, equal to number of hours. You convert it into years. You divide by 24 to change to days, and you divide by 12 to change to days, and then divide by 30 to change. Divide by 365 directly, okay? Directly you can divide this one by 24, you change to day, and then divide by 365 days per year, you convert into years. So it is about 4 years, okay? If you allow only drop by 90%, means you calculate how much is the 10% of drop by 10% only, means allowed up till 90%. So what is the 90% of 94? This is the value we'll put here. So of course it will be much longer duration. Okay, the Q10 method is relying on the value of Qt, and this one used to estimate the effect of a 10-degree rise in temperature on the stability of pharmaceuticals. Q10 is the factor by which the rate constant increase for 10 degrees temperature increase. This is the factor by which the rate constant, means K, increase if the storage temperature increase by 10 degrees. Q10 is the ratio between this is the factor, the ratio between the reaction rates, rate constants, K at certain temperature, and if we increase the temperature by 10 degrees, how much will be the K? So for example, K at 30 degrees and K at 30 plus 10, K at 40 degrees. The ratio between them is the factor that will lead to, is the factor by which the rate constant of degradation increase for a 10 degrees increase in temperature. Q value is usually 2, 3, and 4, depending on the value of activation energy. Okay, these are the values that are usually used in studies. And these represent the energies of activation of the reactions around room temperature. Okay, so these are the activation energies at room temperature. If activation energy for the degradation product is 12.2, usually Q value is 2, means that at each 10-degree increase, the reaction rate constant will increase by double. If the value of activation energy is this value, means that at each 10 degrees increase in temperature, the reaction or the degradation rate will increase by, the degradation rate constant will increase by 3 times, by the factor of 3. Here by factor of 4. This is another equation replacing K by the Arrhenius equation. You know K is log A and then this value divided by temperature. I have temperature 2 and temperature 1. Okay, so this is another form of the equation, and for any change in temperature maybe above 10 degrees, so Q delta T, not Q10. Q10 is Q for the factor for 10 degrees increase. For 20 degrees, for 30 degrees, then it will be the ratio between reaction rate constants at these two different temperatures. And another form is, it will be equal to Q10 to the power delta T divided by 10. So if delta T, for example, is, say, if delta T is, say, 20 degrees, Q10 equal to, Q delta T, Q20 equal to Q10 to the power 20 divided by 10, means equal to Q10 to the power 2. Okay? So Q30 will be Q10 to the power 3 and so on. So this is the factor. The factor change, the change in the reaction rate constant or degradation rate constant with the change in temperature by certain amount. If you change temperature by 40 degrees, then you get a change of the degradation rate by a factor equal to Q10 to the power 4. Change 50 degrees, then equal to the change in the, or the ratio for the reaction rate constant will be equal to the K10 to the power 50 degrees means power 5, okay, and so on. So another form we can get for this, equation is the last equation, T90. This means that the time for the concentration for the content of the drug formulation means the time for the content of the drug formulation to decrease to 90%. At certain temperature, T2 is equal to the time to decrease the content by 10%, means up till 90%. The value of decrease is 10%. The final content will be 90% after you decrease 10%. Times the first temperature divided by Q10 to the power the delta T divided by 10. So here, for example, if you want to calculate, here, for example, how to apply this equation. This equation you have, for example, Q10. You know how much is it? Say, for example, 2. And then you know that, for example, the drug shelf life at 40 degrees, say at 40 degrees, shelf life is 2 years. Then how much will be the shelf life at 30 years, at 30 degrees? Okay, so here shelf life, say for example at 30 degrees will be equal to shelf life at 40 times this temperature 40 degrees divided by Q10 to the power delta T. Delta T is here is 30 minus 40 is minus 10 to Q to the power negative 1. Q to the power divided by 10. So means Q to the power negative 1. Okay. This is how the value change. Okay, then we talk a little about the effect of packaging on stability. Packaging of the drug products is very important when its stability is being considered. So because there may be some interaction between packaging and the drug product or the formulation. So stability study should include packaging, should be the formulation in the final packaging. It means you cannot just produce loose tablets and then store them at certain temperature and then measure the degradation with time. It depends. You find, for example, that your drug is moisture sensitive or light sensitive, you put in a specific package to protect from moisture and then or to protect from light. And then you store at the drug packed already in this package. For example, tablets and blisters, immediate packaging only. Carton box is not necessary. Or for example, solution in ampoules and syrup in glass bottle or plastic bottle. Okay, then you conduct the stability study. So the immediate container and closure, they are important because they affect drug stability. And then here you have to choose the appropriate type of packaging. We have different types of packaging: glass, plastic, rubber, and metal. Rubber is usually the stopper. It's not the whole package. So for example, like vials, you have the closure is the rubber, but the vial itself may be glass, mostly glass, maybe plastic. Some materials or formulations are stored in metals. For example, like spray, we may put in metal canister, right? Glass is the good thing, it is resistant to chemical and physical change, and it is most commonly used material, but there are different types of glass. Some may have alkaline surface that may raise the pH of the product. Ionic radicals present in the drug may precipitate insoluble crystals from the glass. The clarity of the glass permits transmission of high energy wavelength of light, which may accelerate decomposition, because this is always with the normal type of glass. So because of this, there is modified glass. There is glass made from borosilicate. This is type 1 glass that can resist temperature, and same time it doesn't have this kind of reactions or alkaline surface, so contains fewer reactive alkali ions. Okay, and then also there is type 2 glass that there is surface treatment of glass surface with chemicals. This one reduce also the interaction with the formulation inside the glass package, and then prevent the second problem, the ionic radicals interaction with the glass. And then for light transparency or permissibility, can be mixed with opaque materials that will prevent the passage of light. So we make it amber color, so it is suitable to store light sensitive drugs. Transmit light only at wavelengths above 470. Okay, you know that shorter wavelengths means stronger light, more energy light, right? Above 470 means light with less energy that may not affect the drug. When it comes to plastics, they include a wide range of polymers of varying densities and molecular weight. Each possess different physical-chemical characteristics. There are some problems with plastics, like migration of the drug through the plastic into the environment. There will be absorption of the drug into the plastic, and some volatile compounds may even migrate out of the package. And then also they may allow elements from the environment like moisture and oxygen and other gases to enter into the package to reach the formulation. Also some additives that are used for manufacturing of plastic to make it elastic, for example, or give it some properties, they may leach out, means they leak from the container into the drug formulation. These things especially happen more with the number 3 can happen more with liquid formulations. Absorption or adsorption of active drugs or excipients by the plastic may happen. Adsorption means on the surface, absorption means inside the matrix of the plastic. So these all may happen, so we can use there are different types of plastics. They have variable characteristics when it comes to these problems, so we use the suitable one. We will study it more in detail in the pharmaceutical packaging in another course. Metals, as we know, some canisters made from alloys and aluminium tubes may be utilized for containers for creams, for example, or ointments or pastes, emulsions, for aerosols, for example, canisters, for sprays. They may have some corrosion may have to them and may cause precipitation of the drug product. So sometimes we are using laminated, or in many conditions, to isolate the metal from the formulation so that will not interact. They are isolated by inert material. The metal will be laminated, coated with polymer, plastic polymer or epoxy. This may reduce the interaction because these polymers or epoxy are inert materials that will not interact with the formulation. So it is metal from the outside, and from the inside, the surface that will come into contact with the cream or ointment is laminated with a layer of plastic polymer. Okay, rubber is usually used for the stoppers of vials. The problem of rubber is mainly extraction and leaching. So it may absorb some drug ingredients. I may leach some of its contents for rubber to make it more flexible, that will not break. They add some additives in industry. These additives may leach into the drug formulation, same as in plastics. And there are some banned components now because they used to cause some side effects even to the patients. Okay. Some materials like neoprene, butyl or natural rubber in combination with certain epoxy or Teflon or varnish coatings, this reduces the drug container interaction. And pre-treatment before use, like washing and so on, they will remove any particles on the surface, and so it will not introduce particulate matter. Okay, so I think enough to stop by this one today, and then we can complete the remaining part in the last session together. Okay.